All right, so what we've seen with the last two functions, in fact, like if you think of cube root of x, is f of x equals cube root of x, is that function continuous at x equals 0? I should have drawn these ahead of time, but whatever, I didn't. Shipping. All right, here's x equals 0. Is f continuous at x equals 0? And then look at the other function that we had, was x to the 2/3 power, right? So this function, g of x equals x to the 2/3 power. And here's x equals 0 right here, because that's the origin. Is g continuous at x equals 0? Well, is the limit from the left equal to the limit from the right? Yeah, the limit as x approaches 0 equals 0. So in fact, f of 0 equals 0, because cube root of 0 is 0. And that's also what the limit as x approaches 0 of f of x is. So since the function value is equal to the limit, yes, f is continuous at x equals 0. What about g? Well, the limit from the left equals the limit from the right. They both equal 0. Same thing. F of 0 equals 0. So we could ask, is f of 0 undefined? Is there a hole here? We already asked that question. 0 to the 2/3 power is the cube root of x squared. The cube root of 0 squared is 0. It's perfectly well defined. And that's also what the limit from the left and the limit from the right are. So that equals limit as x approaches 0 of f of x. So the function value equals the limit value. So once again, yes. Yes, it is continuous at x equals 0. But f is not differentiable. This is what we talked about before. F is not differentiable at x equals 0. Also, g is not differentiable at x equals 0. And by the way, if you're asked to justify this statement, why? All right, f is not differentiable at x equals 0. Our standard justification for that will be because f has a vertical tangent there meaning at x equals 0. All right, g is not differentiable at x equals 0 because g has a cusp there. All right, and these are the types of justifications that we're going to use for f not differentiable. This is the justification you've already learned for f is continuous. So what we can see here is that f can be continuous but not differentiable. So at a certain point, so even if a function is continuous, the derivative might still not exist. So f can be continuous but not differentiable. All right, well, is the reverse true? Can f be differentiable without being continuous? So it turns out that there's a theorem that if f is differentiable, then f is continuous. All right, now this applies to the entire function or the function at any point or over an interval. So for any, regardless of what type of domain or subset of the domain, any point or set of points where f is differentiable, f is also continuous. That is in your book on page 113. And here's a nice way to say it. Differentiability implies continuity. So remember I said in mathematics, implies means an if-then statement, a rigorous if-then statement, not a vague statement, but implies in mathematics is a rigorous statement. It is in fact this symbol. This symbol is red, implies. F differentiable implies f continuous. All right, if f has a different derivative at x equals a, then f is continuous at x equals a. Now they give a proof of it. The proof is pretty readable and it's fine. I'm not going to spend time on it. It's not important to me. If you find it interesting, go ahead and read it. If you have questions about it, let me know. I'm just going to focus on the result because this result is really important. The AP exam will definitely find ways to find out if you know that because f is differentiable, it would have to be continuous. Now, here's another consequence of that. It means that if f is not continuous, then f is not differentiable. All right, so this is a related statement that we can use a lot, because it essentially gives us a third way that f might be not differentiable, is if f could be discontinuous. All right, a little logic is worth talking about here. This is a statement in the form A implies B, if A then B. All right, this one is the same statement, but it's negated and the order is reversed. Not A, oh, I'm sorry, not B implies not A. This symbol, by the way, is a formal logical symbol for negation. And so a simple way to say that is just not. All right? So A implies B, not B implies not A. The relationship between these two logical statements is called contrapositive. It's a good one to know when you go into your higher math classes. So the contrapositive means if I take an implication and I reverse it and negate it, I'm going to get something true. So to take a simple example, let's say I'm like really naive about umbrellas, okay, and I only take them if it's raining, and if it's not raining, I don't take them, all right? So if I take my umbrella, if it's raining, then I take my umbrella. If I didn't take my umbrella, then it's not raining, right? With us, we see a more sort of mathematical way to say that. If A is prime, if a number is prime, then all right. I could have thought this out beforehand, but I didn't. I'm just thinking of it now. If a number greater than 2 is prime, then that number is odd. If a number is not odd, then it is not a prime greater than 2. Okay. All right, it's called the contrapositive. It means you can turn a function around, you turn a logical implication around and negate it. So by the way, if you're like really a logic nerd, if an implication is true, it always follows that the contrapositive is true. All right. By the way, things like this is not necessarily true. So if A implies B, it does not follow that B implies A. That's called the inverse or the converse. I can't remember. There's an inverse and a converse. I don't remember them. Or, for example, not A implies not B. All right. These things might not be true, even if A implies B is true. But if A implies B is true, then not B implies not A must be true. So you could write that like this, see? A implies B if and only if not B implies not A. All right, that's just a little bit of formal logic nerdism that you might like. If you like thinking about these things, then you like formal logic, which you can study. It's useful in computer programming, and it's also useful in philosophy and logic and a lot of other things. Even things like law, you use contrapositive to prove something anytime you're trying to prove things. All right, so this is our conclusion. If a function is differentiable, then it's continuous. So if it's not continuous, the function is not differentiable. Therefore, we have now cataloged, importantly, 3 ways that a function f could not be differentiable. They are vertical tangent, cusp, and not continuous. Let me put it this way, discontinuity. All right, so we'll talk about that a little bit more, some specific examples next. But by the way, this is our primary takeaway in Chapter 3, Section 2.